Okay, so good morning, everyone. Let us start with lecture 38, and we will be doing probability bounds today. So we have seen multiple random variables in the last class, and you may do some more practice. I will give you some questions for practice. It's important that we complete these bounds. So the first one is union bound. So what is this? This comes from inclusion-exclusion principle. So if you can recall inclusion-exclusion principle, excuse me. Yeah, so from the set theory, then this states that the probability of the union is probability of the sum of the probabilities individually, and then you subtract the intersection, pairwise intersection, and then you add the three tuples intersection, and then you subtract, and then you add, and so on. Okay, so so this is this follows from the inclusion-exclusion principle. Okay, so this from set theory, what we know is like cardinality of the union, right? It's the cardinality of the of, let us say, A union B is cardinality of A plus cardinality of B minus cardinality of A intersection B, right? So this can be generalized, right? So if I want to generalize this, then this will be union over I, AI, and then this will be the cardinality of the individual terms. Okay, so this will be sum of the cardinality of I equal 1 to n of AI. Okay, and then minus, okay, sum of I less than j, and then cardinality of AI intersection AJ, and so on. Okay, and then we have plus, and then we have minus, and so on. So the signs alternate. So this is how this is what is inclusion-exclusion principle. Inclusion-exclusion principle. So that's, we know, for the cardinality, and also it holds for the probability. Okay, so this is the inclusion-exclusion principle for computing the probability of the union. So I think we have proved this before. So one thing to remember is that first term is just the singleton, second term is the intersection of pairwise. Okay, and it's a subtraction here, and then you have to add the intersection of three terms, and then you have to subtract the intersection, all possible intersection of the four terms, and so on. The last intersection of all the AIs. So what does union bound state, right? So union bound states that the probability of union of events is smaller than sum of the first term. Okay, so probability of the union of the events is smaller than the first term. Okay, so the first term seems to be this, right? Okay, so that is for n equals to 2, we have this. Okay, so this is what it's trying to say, because, and this fact is like obvious, right? Because we know that the probability of A union B is probability of A plus probability of B minus probability of A intersection B, right? So this guy is greater than equal to 0. So if I'm going to drop it, so since this guy is equal to this, so this guy is greater than equal to 0. So it must be that this guy must be greater than equal to this guy, because I'm subtracting a positive quantity from here. So that result, this proof is obvious. Okay, so but the idea is like this proof should generalize to general case. So in other words, if I take n a general case, then what I claim is probability of union of AI, I1 to n, will be less than equal to sum of the probability of the AIs. Okay, I equal 1 to n. Okay, so that will be the general case. Okay, so and the proof for the general case also would hold in the same way like I said before. So these are like sum of the positive quantities, and then you are subtracting that. So if you drop that, then the sum must be larger than the left-hand side. So this union bound proof is rather straightforward. Okay. Now there is something called generalized union bound, or so-called Bonferroni inequalities, some Italian name. So let A1, A2, A and B events. Then the first one is fine. This is the union bound. Okay, so union bound that we have seen before. Second one, you see the inequality changed, right? So this was less than equal to, and now it became greater than equal to. And what changed here? Well, I added the second term now, right? So if I add the second term, then the inequality changes. If I add the third term, okay, then inequality should change. This is mistake here. Okay, so actually it keeps flipping. The inequality keeps flipping. First is less than equal to, is greater than equal to. You add the third term, then it's less than equal to. Then if you add the fourth term, it's greater than equal to, and so on. Okay, so this is called generalized union bound or Bonferroni inequality. So what it says is that if we stop at the second term, then we obtain the lower bound. Okay, so this acts like a lower bound because it's the lower value. And if we stop at the third term, in this case, then we obtain an upper bound. Okay, so as I said, there was a mistake here. So this now term acts like an upper bound. So this can be rather useful in estimating the probabilities. Okay, we are talking about estimations now, right? I want on my probability values. Okay, or yeah, so if I know this, then I know I may find something for this. So these are a good way to estimate. In general, we can write, if we write odd number of terms, then we get an upper bound. So odd number of term, one term, and this is the 3 terms. Okay, so we get an upper bound. So this is an upper bound, this is an upper bound for odd number of terms, and for even number of terms, we get a lower bound. And here we get upper bound. Okay, here also you get upper bound. Okay, so if we write even number of terms, we get a lower bound. So that's what is the generalized union bound. And I'm going to skip this example of this. Maybe you can try this. Okay, so let me move to some other important inequalities. There is so-called Markov inequality and Chebyshev inequality. So these are both Russians. You will hear them more. Markov decision process are there. So I won't have time to go into this. Obviously, in the first probability course, you can't do everything. So there is something called Markov process. Okay, so random process is topic taught in more advanced probability courses. And you have Markov process, and then you have concepts of MDP, and things are used in some variants of machine learning. For instance, if you want to do reinforcement learning to make the robot learn something, right? So these are like important concepts, and these things will be taught to you in the courses in future. Okay, the random processes and so on. Okay, so let us see Markov inequality. This is not about random process now. Here it's about some inequality, which is often useful. So if x is any non-negative random variable, okay, so it's a non-negative. Okay, that's important because random variable, we know it can take negative value also. Okay, I can define heads as -1 and tails as +1, right? It doesn't stop me from defining minus and +1 values. Okay, so for me, this could be equivalent to head and this could be equivalent to tail. Okay, so but then this will not work here. So here we want x to be non-negative random variable. Okay, so another way to say is like, can you transform this into something like, yeah, so you may have to redefine x to use Markov inequality in cases some negative values. Okay, so redefine the x with some y variable, and that for that y variable -1 corresponds like 0 and +1 corresponds to +1 only. Okay, so it's non-negative, so 0 may be allowed. Okay, so for x, any non-negative random variable, so this may not be a strict restriction. Okay, you may get away with this by redefining. So then, so Markov inequality says the following, then the probability that x greater than equal to a will be less than equal to expectation of x divided by a. Okay, so sometimes you are interested in computing the probabilities like this, and you would like to know what could be the upper bound on this. So this is the upper bound. Okay, it may be a loose upper bound, it may be very far and so on. That's we are not talking about, but this is a upper bound. Okay, there is no unique upper bound. In least of all upper bound is called the supremum, right? So least of all upper, so you have done real analysis like LUB, least of all the upper bound is defined as supremum. This is unique. This is unique. But here when we talk about a upper bound, it may not be unique. Obviously this +1 is also an upper bound, right? Okay. So this inequality is a Markov, this called Markov inequality. Very simple inequality. If you have a hold of the expectation of x, then an a is already given to you because someone gave you a problem to estimate this. So a is known to you, assuming that the distribution x is known to you, or even if its distribution is not known, you can find the expectation, then you have some estimate. Okay, it's about an estimate. So moreover, let b greater than 0, then so we are moving to some other variant now, Chebyshev. Okay, so this was the Markov. If b greater than 0, then if you want to estimate something like this, x minus expectation of x greater than equal to b, then this is bounded by variance of x divided by b square. Obviously, b is a constant here. So it's like your bound is proportional on variance, and here your bound is proportional on the expectation. Okay, so this is given a new name. So this is the above inequality is called Chebyshev inequality, and states that the difference between x and ex is bounded by variance. Okay, but that is kind of expected, right? Because from the probability distribution, we know that this is like the spread is given by this variance and so on. So how far my x is from the expected must depend on the variance, the spread of the data. Okay, the difference of x from the expectancy must be bounded by the spread of x. So that looks intuitive. Okay, so what do we have now? So can we like prove the Chebyshev inequality? Okay, so can we prove Chebyshev inequality assuming that the Markov inequality holds? Okay, so let us try to prove the Chebyshev inequality. So proof of Chebyshev inequality. So what we will do is that we will define a random variable. So define a random variable y is equal to x minus expectation of x whole squared. Okay, and then this one thing is like it will be by doing this, what I'm making sure that it's non-negative is non-negative. Okay, that's fine. So one thing is like what is known to me is like Markov. So because as such x minus ex was not guaranteed to be non-negative. Okay, so if I do this and square it, then it's guaranteed to be non-negative. So that's a thing that I'm going to use now. Okay, so we can apply Markov. Okay, so for any positive real number b, the Markov. Yeah, so I want to intend to use Markov, but I want to arrive at Chebyshev, so I will choose some constant as b here. Okay, so for any positive real number b, we have, so for any positive real number b, we have what probability that y greater than equal to b square, assuming that y is this and which is non-negative. So I am allowed to use the Markov. Okay, so this will be expectation of y greater than equal to b, right? So it will be expectation of y by b, right? So expectation of y by b, right? So this is from the Markov, right? So this is Markov. Okay, and what is expectation of y, right? So let us see what is expectation of y. Expectation of y is expectation of this guy. This is the y. So x minus ex whole squared, right? So, but this is nothing but the variance, right? Because this is how the variance is defined for random variable x. So this is variance of x actually. Okay, so that's by definition, right? Now, so I can replace this by that, right? So this implies probability that y greater than equal to b squared is probability that. Now I can substitute the y here explicitly now. In place of y, I can substitute this whole square is greater than equal to b squared. Okay. So remember there is a mod here, right? So we can do that here also because this is square is greater than equal to some square. So this is the same thing as saying that probably that mod of the probability that mod of x minus expectation of x. Okay, so x x minus expectation of x mod is greater than equal to b. This is the same thing, right? So yeah, so this is equal to this, and this will be less than equal to variance. So expectation is this here, right? So expectation of y was variance of x. So this is variance of x by b. Okay, or b squared, right? So we missed squared here. Yeah, so b squared. Okay, so this is less than equal to expectation of y, which was variance of which was variance of x by b square, and this I believe is the Chebyshev, right? So probability that x minus ax greater than equal to b is greater than equal to variance of x by b squared. Okay, that's done, right? So which is the Chebyshev inequality. Okay, so that's what we are supposed to prove. Okay, now what are the examples of Markov inequality? Let us see. So let us see how we can employ. So let x be a binomial. Okay, binomial with n trials and of obtaining a head is p. Then using Markov inequality, find an upper bound on probability that x greater than equal to alpha n, where alpha is some arbitrary between p. P stands for probability. So I can choose alpha between p and 1, let us say. Then so find an upper bound. So I have to find an upper bound and verify this bound for p equals to half and alpha equals to, and then later I have to verify whether the bound I obtained was a valid bound. Okay, so we are supposed to use a Markov inequality, right? So Markov inequality, so Markov inequality told us probability that x greater than equal to a is less than equal to expectation of x divided. Okay, so that's the Markov inequality. So probability that x greater than equal to a is less than equal to expectation of x by a, right? Okay, I'm sorry. So here we are. So first of all, x follows the binomial, right? So x is a non-negative. Okay, so x is a non-negative random variable. So that's the first step we have. So x is non-negative random variable, and expectation of the binomial is, we know it's NP, right? So expectation of binomial is NP, right? Okay, this is P, right? Okay. So, okay, so we can apply the Markov directly now. So applying Markov. So we obtain probability that x greater than equal to alpha n is, so this is the quantity we were asked to find a bound on. So this will be expectation of x divided by alpha n, right? That's the Markov. And this will be expectation of x is np by alpha n. So n goes away. So p by alpha. Okay, that's the upper bound. And we are supposed to check for p equals to half and p equals to, so verify, right? So p is equal to half and alpha equal to 3 by 2. We basically substitute this, right? So this implies probability that x greater than equal to alpha 3 by 2 times 1 by 2 is less than equal to p is half by alpha is 3 by 2. P is, yeah, so this, oh, sorry, what is going on here? There should be n here, right? Why did I do p here? Okay, sorry. This is not np, right? So this is so alpha, right? Alpha is 3 by 2 and n is n, right? So that remains. Okay, and yeah, so this is less equal to p is half. Okay, so p is half. Oh, 3 by 4 actually, right? So alpha is 3 by 4. Okay, and this turns out to be 2 by 3. Right, because 2 gets 4 gets cancelled. Okay, so this is the answer we have. So probability that x greater than equal to 3 by 2 n will be bounded by this, upper bounded by this. Okay, now what will happen if I apply the Chebyshev inequality on the same problem? So let us see, x is still binomial. Now I'm asked to apply Chebyshev and find an upper bound on this same quantity, but now using Chebyshev. Okay, so Chebyshev inequality, what did it tell us? Right, so mod of x minus probability that mod of x minus expectation of x, okay, is less than equal to variance of x by, so this sorry, so this is greater than equal to b, is here b, right? So this was Chebyshev inequality, right? So okay, so it will give a bound on but what we are supposed to find is this, right? Okay, so let us see what we can do here. So probability that x greater than equal to alpha n, if I subtract np from the both sides, right? So if I subtract np, so the inequality doesn't change. So alpha n minus np. So this will be less than equal to, now if I change this to mod, okay, and then it will give me more possibilities. In other words, I am going to enlarge this probability. So if I'm going to use a mod of x minus np, okay, I'm essentially going to increase, because I am increasing my sample space. Here it was only this guy less than equal to this, but if I'm doing mod, then this is saying that I'm also taking x minus np less than equal to this, right? So so I'm going to definitely increase my probability here. So n alpha minus np, or alpha n, same thing. Okay, and yeah, so the reason why we did this is because Chebyshev can be used here now. Okay, so these are the tricks that we did, and then the reason why we subtracted from NP is like NP is the expectation of the binomial, right? So expectation of the x is NP, and we wanted to put this in the Chebyshev form. So this is of the form x minus expectation of x. Okay, so this is in perfectly in that form, and then this is the b role of the b, right? So this will be so this will be further less than equal to, possibly further less than variance of x, and then divided by the b squared, right? So there's a mistake here, right? So this is b squared here. So n alpha minus np squared. Okay, So variance of the binomial was p1 minus p, and this is it's like n square comes out, right? So yeah, so n squared comes out, and alpha minus p squared, right? Variance of binomial was n also, right? Yeah, so variance, there is one more n here, and n gets cancelled. So this is p1 minus p divided by n alpha minus p whole squared, right? And one can again verify this for alpha equals to half. That was the next part of the question. So I leave it up to you to verify this. Okay, there is something called Chernoff bounds. Okay, again, yet another Russian. Okay, so Chernoff bound, let's see. So these are all bounds. Okay, these are called probability bounds. So let x be a random variable and a be some real number. Then define this. What was this, if you recall? Moment generating function, right? Moment generating function, right? So if you recall this, right? Moment generating function. Okay. So this is a known quantity. So moment generating function, nothing to be scared of. It's just expectation of the exponential of Sx, okay, where x is the given random variable. So we know exponential of Sx using the Taylor series, right? So 1 plus 1 by Sx plus 1 by, okay, so exponential 1 by S square, X square, something like that, right? So expansion of the exponential in the Taylor series. Okay, so that we know. It's just that now I have to take expectation here. So it will be expectation of this guy and so on. Okay. Will the moment generating function, and then the following holds. So these are bounds that use moment generating function. That's the trick here. So the probability that x greater than equal to a will be bounded by something like this, and probability that x less than equal to a will be bounded by something like this. For s less than 0, okay. So for s less than 0, we are talking about less than equal to, okay, because it's negative here, and then here for s greater than 0, the first inequality holds. Okay, the above holds for any s. So they are a case by case basis. So for s greater than 0, what we know is like this serves as an upper bound for all s. For all s, this serves an upper bound. So to find the strict case, you better minimize this over all s, right? So if you minimize this over s, obviously the inequality keeps holding, but this is the better bound now. Okay, we say a bound better, or like let us say even better word is strict. Stricter bound or stronger bound. Okay, so strong bound. So this is stronger. You have found the best possible, least possible value of the upper bound. So perhaps this will act like a supremum. Okay, and then similarly here. You can also take a minimum over this, but remember that here s is less than 0 and here s is greater than 0. Okay, so yeah, this follows from here itself. Now the question is, how does this follow? Okay, and this follows from by just observing some facts in the sense like, if you see this quantity x greater than equal to a, then I can raise it to exponential power, both the sides, right? So a is greater than equal to b. It's the same. From here, this inequality can raise the exponent, and then inequality doesn't change. So e to the a is greater than equal to e to the b. If a b is greater than 0, right? Then I can raise it to the exponential power, and then this remains the case, right? So this is the trick we are going to use here. Okay, so that we get hold of these terms, exponential to the power. And then, yeah, and then we are supposed to see what would be this case. So this case seems to be like, okay, because I have x greater than equal to a, so e to the x a, sorry, e to the s. So I have to raise it by s power. Okay, so x greater than equal to a is same as s times x greater than equal to s a. Then I raise exponential power, so it will be e to the s a. So you get the idea what is going to happen. So So this guy will be if I take expectation of, then this guy will be this moment generating function. Okay. So we have some initial plan. Let us now get through this. Okay. So we will try to do this in the next page. So X is a random variable and A is a real number. Then we can write. So we can write probability that X greater than equal to A is same thing as I explained, is probability that E to the is greater than equal to E to the SA, because this inequality is same as this inequality. The condition that X greater than equal to A is the same condition as, because if I have to solve this, I will take a logarithm and then it will give me the same inequality. So they generate the same sample space. That's what I'm trying to say. So hence the probability did not change. Okay. So for S greater than A, when I raise it to the positive power, obviously. Okay. And similarly for S less than A, so probability that X less than equal to A will be probability that E to the Sx is greater than equal to E to the Sa. For S less than, sorry, why I'm saying 0, so it's greater than 0. Okay, so let me do this in a clean way. So this is S greater than 0 and this is S less than 0. Okay, so if I'm raising it to the negative power, right? So this, and here I have a less than equal to, then the inequality flips, right? So A less than B, and then if I and if they're like if they were like negative, then if I raise to the power of E, so if A and B were negative quantities, then if I raise power, then inequality exponential, and then the inequality flips, right? So these are inequality properties. So these are the things we have. Now, what do we have next? So the next thing we have is we want to use Markov here, and let us assume that. So first of all, to use Markov, is this a positive random variable? Yes, exponential of anything is positive, right? So since exponential of Sx is always positive random variable for all S in R, okay, regardless of S is negative or positive, exponential is always positive. So we can write probability that X greater than equal to A is probability that E to the Sx is greater than A. I'm just copying over for the moment. And this is less than, now I'm applying the Markov here. So applying the Markov, I have, what was that? Expectation of this, right? So expectation of e to the Sx divided by the value e to the Sa, right? So this is by Markov. So yeah, so this is similarly. So this I can like what was the question was asking, wrote this in this form. So I will just take e to the minus Sa, then expectation of e to the Sx, but this is the moment, right? So it is mxs, right? Okay, so similarly for S less than 0, you can try. Okay, same thing. Okay, so now so that's the Chernoff bound we saw. What we proved just now is the Chernoff bound. And so now the question is, assuming the same example that we had before, what would be the value for the Chernoff bound? Okay, so everything is the same. Now what we will get with the Chernoff bound, right? So the Chernoff bound requires the moment generating function. So moment generating function for binomial is something I leave it up to you to verify that for that, let me start from here, okay? So for X binomial and P, okay? So moment generating function is known to be like this. This is, you can take this as an exercise if you have not done this before. So moment generating function of a binomial is given by P e to the S plus Qn, okay, where Q is 1 minus P. Okay, so I have now, like, I remember this and then I just recall this, and in your case, like, you may actually try to prove this, okay, explicitly. Now the Chernoff bound, right? So that's the Chernoff bound for probability that the main thing to identify the moment generating function of the underlying distribution. So now we can write that X is greater than or equal to alpha n will be less than or equal. So let us apply that Chernoff bound with that minimum possible value, right? So this will be minimum of S over S greater than 0, e to the minus SA and mx s. This was the so here we put the value. So minimum S greater than 0, e to the minus SA is as it is, and this is the moment generating part that we put it here. So e to the S plus Qn. Okay, so this is like finding a minima of a function, right? So finding a minima of a function, so it is like some function fs, right? Now, how do we find minima of a function using calculus? We differentiate this and we equate it to 0. And obviously, you have to take the second derivative test. So have is to find minimum of over s greater than 0 of the function fs. Okay, so recall from calculus that the minima is found by first doing the derivative with respect to s, equating it to 0, and solve for s to obtain critical points, right? Critical points. So these are the critical points. So that's where the derivative is going to be 0, right? So it could be many cases where derivative is going to be 0, right? So your function could be like this. So derivative is going to be 0 here. So this is your S1. Here you have S2. Derivative 0 here. So here you have S3. And here you have S4. Here you have S5 and so on, right? So S seems to be S1, S2, S4, S3, S4, and so on. So these are the critical points here. The gradient has become flat, but remember you have to find the minima, right? So minima are the places where actually these guys, right? So one of these guys, okay? So tangent becomes flat as both maxima and minimum, but we are supposed to find the minima. So to characterize these points, we need to take the double derivative test. So double derivative test means that if f double prime s is at s, even okay, equal will create some issue because we may get into saddle point. So let us say if it is greater than 0, then what do we mean, right? So if the rate of change of tangent is increasing, so that's the case where rate of change of tangent is increasing. Those are characterized by the minima, right? So this implies s equal to si is minima or the local minima. And similarly, if f double prime s equal to si is less than 0, this implies s equal to si is local maxima. Okay, so there are two possible cases. If it is equal to 0, then you have to go for further derivative test and so on. So this is something we recall from calculus. Now, in our case, we'd have to take the derivative of this fs, right? So the first, and then we are supposed to go to the second derivative test and also make sure that it's greater than 0 for a minima, right? So there are a few steps I'm going to skip here, and I leave this as an exercise for you. What I'm claiming is that the derivative where it's equal to 0 is actually the minimum. Okay, so what I'm going to do is to take the f prime s, which is d by ds of e to the minus sa and p e to the s plus q n equal to 0. So if you solve for this, so these are like small things I'm leaving up to you. So if you solve for this, then to save some time, I have noted this down already. So aq by np and 1 minus alpha. Okay, so this is what you will get. And I also claim that this will be the minima. In other words, the one more step that you are left with is to go ahead and take do the double derivative. Okay, so first of all, I'm saying that this is the only like for s, right? You will take may not have to explicitly solve because maybe in the double prime you will be left with es, so it's better to keep it in es form, and then you substitute it here, and then you will you have to prove that this is greater than 0, and then you claim that that s for which es is this is the minima. Okay, so these are the second derivative part I'm leaving up to you. Okay, so I claim already right now that assuming that we have done this, es, the s for which es is this is the minimizing value of this, okay, of star. Okay, and then we will use the Chernoff bond. Okay, so from before, from previous slide, previous slide, we had e to the s is aq divided by np 1 minus alpha, and check that this is minima. Okay, and then okay, now by using the Chernoff bound, because this example was to use Chernoff bound, right? So using the Chernoff bound, what we have, probability that x greater than equal to alpha n, this is what we are supposed to find for the binomial, is less than equal to, and what was that Chernoff bound? E to the minus sa, right? E to the minus s. So this is e to the minus sa, right? So x greater than equal to a. In our case, a is that alpha n, right? E to the minus sa mxs. So e to the minus s a. Okay, so let me write down probably that s greater than equal to a is e to the minus sa mxs, right? Okay, so in our case, a takes the role of alpha n, right? So a takes the role of alpha n, and mxs, right? So mxs, we know, for we have written here, this is the mxs, is p e to the s plus q to the n. P e to the s plus q to the power n. Okay, so that's the mxs. Okay, and then we are like supposed to we may be able to like simplify this, I believe, by substituting these values and so on. Okay, so es values are known to us and they can be substituted here. Alpha and n are given to us anyway, p and q are given to us. So that's just a formality now to simplify this further. So this is the bound that we get using Chernoff bound. Okay, that was an example of Chernoff bound. So we can we have done we have seen a Markov. It's a matter of, this example is about just compare these, which is the strict, which is the less strict, and so on. So this is something I leave it up to you to find out which bound looks like a stricter bound and so on. It seems like the more advanced bounds like Chernoff bound and so on should give us more stricter bound. Okay, so that's something I leave it up to you. We have results for all this. Now it's about comparing them. Okay, there is something called Cauchy-Schwarz inequality. If you may have seen in linear algebra, okay, in the inner product spaces, So this is taught in linear algebra in inner product spaces. And that states that for any two random variable x and y, expectation of xy, the product, is less than or equal to expectation of x square, expectation of y square, where the equality holds if and only if x is some multiple of y. Okay, so this is very similar to the inner product case, right? So in the inner product space, you substitute this by a inner product, right? So inner product of x, y, so that's the inner product, is less than or equal to square root of inner product of xx, sorry, xx and yy. Okay, so that's the Cauchy-Schwarz inequality, right? And here we also put a mod here actually. So this is the Cauchy-Schwarz inequality, but the only problem here now is that now it's written in this form and there are expectations here involved. Okay, so we need to do a little bit before we can establish this. Okay, so this is what we are supposed to prove. Let us try to establish this Cauchy-Schwarz inequality. And yeah, and we also have that the inequality holds, equality holds if x is alpha y. And that in the vector space case, it was the same thing. The equality holds when x is a scalar multiple of y. Okay, the results are very similar. And on the left is the Cauchy, the very well-renowned French mathematician, and then you have Schwarz. There are two Schwarz actually, one guy with T and one with just Z. So this guy is also French actually, Hermann Schwarz. Okay. So yeah, so this is named after these guys. Okay. Now let us try to prove this. So if we try to prove this, we have to do some trick. Okay. Trick in the sense that I would like to use some existing inequality and prove on the basis of that. Okay. So to do that, maybe let us say I want to use a Markov. Okay, so I may want to define some non-negative random variable from here. So let me try to prove this. And so what are the steps? So the first step I will do is that define a random variable w is equal to x minus alpha y whole squared. So clearly w is non-negative because of the square. So non-negative random variable for any alpha actually, for any alpha. So thus this implies 0 less than equal to, since this is a non-negative, the expectation is greater than equal to 0, right? So expectation greater than equal to 0. Come back to the known variables x and y. Okay, so now I apply the linearity, right? So let us continue with the right hand side here. So this will be expectation of x square minus 2 alpha expectation of xy plus alpha square expectation of y square. I have jumped one step here. So let us define some function f of alpha to be this guy. So let us define this to be f of alpha here. Okay, so let me move this. Okay, then obviously f of alpha is greater than equal to 0. That's clear. What will happen if f of alpha is 0? Okay, so if f of alpha is going to be 0 for some alpha, obviously, then what happens? Then what we have is that expectation of w, which is, so alpha is 0. So f of alpha is 0, right? Okay, if f of alpha is 0, then what we have is that, so f of alpha was nothing but E of w. So E of w, which was defined to be E of x minus alpha y whole square, that is going to be 0. And so this would imply what, right? So expectation of x minus alpha y whole square is 0, right? So what does this imply? This implies that x is equal to alpha y with probability 1, right? So we can write that x is equal to alpha y, okay, because this is expectation, right? So we have to include this additional word that with probability 1. Okay, So if the difference of square of the difference of two random variable is expectation is 0, then it's with probability we can say that they are matching. Okay. In other words, x is equal to alpha y. Okay. Now to prove the Cauchy-Schwarz, we choose alpha to be, so to prove Cauchy-Schwarz, choose alpha to be expectation of xy by expectation of y square. Okay, and with this choice it should work out. Okay, so let us see. We start with where we left last time. So 0 is less than equal to expectation of x square minus 2 alpha. Just I copy over here. Okay, so expectation xy plus alpha square expectation of y. Okay, so expectation of y squared. And okay, what do we have now? So I intend to use this alpha and put it here, right? So this will be expectation of x square minus 2. So alpha I substituting, right? So xy divided by expectation of y squared, and then multiplying with expectation of xy, and then plus alpha square, right? So alpha square, again expectation of xy whole square divided by yeah, expectation of y squared, and then whole squared, and then it is multiplying with expectation of y squared. Okay, so if we simplify this further, right? So what do we get if we simplify this further? So expectation of y square 1 gets cancelled here. Okay, and what do we have? So this implies expectation of xy squared I can see. Okay, and yeah, expectation xy square is here. So there is only one expectation of xy square by expectation xy square left, right? So this is expectation of x square minus, so this is 2 expectation of x square divided by expectation of x square. There is 1 expectation x square divided, so this will be minus of expectation of xy whole square by expectation of x square. So this is greater than equal to 0, right? So this follows from here. Okay, so this implies that expectation of y whole square is less than equal to expectation of xy square is less than equal to, okay, expectation of x square, expectation of y square. Okay, and if I want to, it is allowed to provide a mod here. So this is mod of expectation of xy is less than equal to square root of expectation of x square and then expectation of y square. Okay, so this is the same thing. So that's what we have, right? So this is what we were supposed to prove, and if the if they are going to be 0, right? So if the expectation is going to be, the equality will hold. So when will this equality hold, right? So when will this equality hold, right? So this equality holds when f alpha is 0, right? So when f alpha is 0, when exactly we have already shown this before. Okay, so when is this? So equality holds exactly when f of alpha is 0, and that we already worked out that it is the case when x is equal to alpha y. Okay, with probability 1. So that we have already shown. So one can have some examples of Cauchy-Schwarz or the application of the Cauchy-Schwarz inequality. And one application is like where we prove that the correlation is less than equal to 1. Okay, using the Cauchy-Schwarz. So this is a straightforward implication of that because if I define u is x minus expectation of x by sigma x and v to be y minus expectation of y by sigma y, then expectation of u and expectation of v is 0, the way it is defined, and the variance of u and variance are there like so. This is by Cauchy-Schwarz, it is less than equal to expectation of u square, expectation of v squared, right? So this is normal with mean 0. So this is variance. So variance is 1, 1. So this is like less than equal to 1. So this guy is less than equal to 1. And what we know is that correlation coefficient is covariance of xy divided by standard deviations. So covariance will be, in this case, will be xy minus expectation of x and then expectation of y, right? So this is what we have, right? And then this is sigma x, sigma y. Now apply this on uv. So uv is expectation of xy, right? uv. So uv is like less than equal to 1, right? So this is like covariance of so this is like expectation of uv minus expectation of u, expectation of v divided by 1 times 1. Now these guys are 0, these guys are 0, and this is uv is less than equal to 1, right? So this is less than equal to 1. Okay, so that's how like one can actually prove this, and then this part also you can try. Okay, so with this I will stop here. Okay, so in the next class we are supposed to do central limit theorem, law of large number. These are just couple of lines of statements, and then we will go to statistical inference. For the last 3 class we will do statistical inference, starting with classical and then Bayesian, and that will end the syllabus. Okay, then with that I will stop. Okay, have a nice day. Bye.